Let's summarize what we've covered so far. We've said if a function is continuous, and we're looking specifically at a closed interval, then the function will have absolute maximum and minimum values. And our candidates for those absolute maximum and minimum values are the endpoints of the closed interval, critical points where the first derivative is equal to 0, and critical points where the first derivative does not exist. Okay, those are the rules of the game so far. Let's do a couple of easy examples just to get a feel for how this stuff works in real problems. So let's start with a simple parabola. This is y equals x squared minus 2x minus 3. And I picked a parabola just because this is a shape that we know reasonably well without doing any calculus, without doing any deeper analysis. We can figure out things like it crosses the x-axis at -1 and at +3. It's got a vertical intercept at -3. So we already know a lot about this curve just because it's a very simple curve. We'll look at this on a bounded interval, closed interval from 0 to, let's say, 4. And we want to find absolute minimum, absolute maximum. Okay, let's make a list of candidates. I'll go back to my list. One category of candidates is endpoints of the closed interval. Those are both definitely candidates for absolute maximum, absolute minimum. We can trace down where those function values exist. There's one. Another one is way up here. Next item on the list is critical points where the first derivative is equal to 0. Well, let's mess with the first derivative of this function. Again, you ought to be able to find the first derivative of this without any sweat by now. Y prime is 2x minus 2. If I set that equal to 0, that means 2x minus 2 is equal to 0. Do a tiny bit of algebra, and you find x equals 1. Well, sure enough, 1's roughly there. And if I trace that point down, you can imagine that I've got a tangent line right here where its slope is 0, which means my first derivative is 0. And so that's a candidate for being an absolute maximum, absolute minimum. We do have this third category, critical points where the first derivative does not exist, but let's look at the first derivative. I don't think there's any x value, any real x value I could plug in there that'll make the first derivative not exist. So in this case, that third category, we've got no results. Okay, so we've got three candidates here, x equals 0, x equals 4, x equals 1. How do we decide which one is the absolute maximum and which one's the absolute minimum? You can eyeball the graph and just tell, but really it's sort of a brute force effort. We're simply going to take each of these x values and plug them into the original equation and see what results we get. The very highest of those will be the absolute maximum. The very lowest of those will be the absolute minimum. So let's do that real quick. If I plug 0 into my function, I get 0 squared minus 2 times 0 minus 3. I get -3. If I do f of 4, 4 squared is 16, minus 2 times 4, that's 8, minus 3. It looks like I get 5. And lastly, if I do f of 1, If I plug a 1 into this equation, I get 1 squared minus 2 times 1 minus 3 it looks like I get negative 4. So of these three values, this one's pretty good, but this one's even smaller. And no question, that's my highest value. So there you go. That's a fairly straightforward problem, and that uses most of the points we've talked about above. Let's do another type of problem. In this one, I won't even give you the curve first. We'll just talk about the equation. Y equals x to the 1/3 minus x. And we want to find critical points, which means we want to find where the first derivative is equal to 0 or where the first derivative does not exist. Either way, we start by finding the first derivative. This shouldn't be much of a challenge for you. It's 1/3 x to the negative 2/3 minus, and the first derivative of x is just 1. Okay, so we want to find where this first derivative is equal to 0. Okay, so if I move the 1 to the other side and multiply both sides by 3 to clear out that fraction, I get x to the negative 2/3 equals 3. Okay, now this is going to begin to tax your algebra skills a little bit. I'd like to deal with that negative sign, so I'm going to raise both sides to the negative 1 power. And that'll give me an x to the positive 2/3 over here, and a 1/3 on that side. Next, I'd like to get rid of this third power exponent, so I'm going to cube both sides of the equation. And then I'm going to take the square root of both sides of the equation. Now, let's not forget this plus minus sign. That's pretty important. When I take the square root of something, my answer is potentially either positive or negative. And this is roughly 0.19. Okay, so that covers the case where the first derivative is equal to 0. Now let's deal with the first derivative being does not exist. So my first derivative from above is that. I'm going to massage this a little bit. I'll make this first expression look like a fraction. And then I'd really like to combine these two into a single quotient. So I'll find a common denominator. And now I can push this together into one fraction. Okay, now that I've got this as one big quotient, this expression goes to goes to does not exist when the denominator goes to 0. So let's just pull out the denominator and set it equal to 0, because that's what will make this entire expression go to does not exist. A little bit of algebra will show me that the result is x equals 0. So this is another critical point. We don't know for sure if it's an absolute maximum or an absolute minimum, but it is at least a critical point along with these two x values, positive 0.19, negative 0.19. So those are the critical points of that function.